Well, I made a mistake. I made a dry Irish stout. Was that the mistake? I don't know. I don't know if I like dry Irish stout. The two commercial stouts that I normally drink that other people maybe around the world might be aware of are Guinness and Murphy's Irish Stout. Murphy's is kind of sweet. It's definitely not dry, and that's what I like about it. I like it a little bit better than Guinness. Guinness has a bit more bitter to it, but it's not as sweet. And I still love it. I just don't like it quite as much as I like Murphy's. But I decided to try a dry Irish Stout, making one on my own here. And the mistake I made was that it had some steeping grains. Let's see what they were. UK roasted barley, 12 ounces, so 3/4 pound of that. 1 pound of flaked barley, 4 ounces of acid malt, and 4 ounces of UK black malt. And, of course, you steep those at in Fahrenheit at about 150 degrees, it says, for 30 minutes. My mistake, I must have been thinking of a few things at once and not paying close enough attention. I brought my water to a boil, added the steeping grains, left them there for 30 minutes, and it was only when I pulled them out and I noticed, hey, wait a minute, this water's boiling, that I realized that I had put them in boiling water and had them boiling for all of that time. So, now it's time for me to do a taste test on it, and it can be kind of an experiment to maybe find out what kind of an effect it has. I say maybe because if there is some strange off flavor to it, I would only be guessing that it's due to for steeping the grains in too hot of water. It could have to do with anything. I asked someone from the 17 Brew Crew forum what he thought, and he says, wow, those are the worst grains possible for you to have done that with. I asked the person at the brew shop where I bought the kit from, and that guy says, you know, given that there's so much roasted grain in here to begin with, it might not make any difference at all. I looked it up in John Palmer's book, How to Brew, and what he says is that there are enzymes in the grain, which if you get it above the steeping temperature, you kill the enzymes which are necessary for something. I don't remember what. I guess I'll have to look that up and edit it in a little later. But I had this, let's see when I brewed it. I brewed it, looks like on the 24th, so Christmas Eve. And I kegged it on the 7th, which was... No, I didn't keg it on the 7th. I kegged it last night, which would have been the 8th. And it's been just 18 hours since then, roughly, 18 or 19 hours, in the keg under 30 pounds of pressure in a refrigerator. Is that enough to carbonate it? Of course not. So what I did was I did some shake carbonation on it, grabbed the top of the thing and just rocked it back and forth, and you could really hear those bubbles going into the solution from the CO2 tank that I have hooked up to the liquid side. So you could hear it bubbling up from the bottom. Of course, it just became part of the atmosphere at that point inside the keg. It didn't actually diffuse immediately into the beer. So I've waited about an hour and a half for at least some amount of the carbon dioxide that I just added to make its way into the beer. Notice I called it shake carbonate. I didn't call it force carbonate. I hate that term. I don't know what people think they mean when they say force carbonate. What are they forcing? The carbonation process isn't any different when you shake it than it is when you just put it under pressure and leave it overnight. The difference is when you just put it under pressure and leave it overnight, there's a great big bubble, we'll call it, of atmosphere on top of the keg. It's flat, right, on top of the beer. And you can think of the carbon dioxide molecules, just metaphorically, as like being fish that dive down into the beer. And they It's just every time, think of it like this, every time one of these molecules crashes into the beer, it goes into the beer, it dives in. It doesn't like bounce off and go around again. It actually goes into the beer. But inside the beer, there's also carbon dioxide, which is bouncing out. Eventually it reaches something called dynamic equilibrium, which is when there's just as many molecules, molecules diving into the beer as there are jumping out. Now there's other things in there too. There's, like for example, water vapor in there. Water is evaporating out and condensing in. It's in dynamic equilibrium as well. Eventually you get some pressure in there on top of the tank, and each one of these different things has a partial pressure, which all add up to the total pressure. In any case, right now, because I put all that CO2 in there, I'm sure it's not at dynamic equilibrium yet. It's probably still got way more carbon dioxide up in the atmosphere currently diving into the beer than is coming up. In other words, there's no need to add any more until it actually goes down, but I'm not going to wait. But what happens when you shake carbonate it is, you've got this bubble. When you start off, you've got this bubble on top of the tank. It's just sort of flat, and the stuff is diving in there. But what would happen if you could somehow separate that bubble into two bubbles, just layered inside the tank? So you have beer at the bottom, then a bubble, and then beer at the top. Well, now you've got actually three surface areas. You've got the bubble, the bottom of the bottom bubble, the top of the bottom bubble, then you have beer, and then you have the top of, or the bottom of the top bubble, right? If you can just picture how these layers go in your mind. So you have 3 times the surface area, which means that your beer would carbonate 3 times as fast. It would only take 1/3 as long for it to carbonate, right? Well, when you shake a beer, you're creating, instead of having that great big bubble at the top, which is just, you know, the surface of the beer, you shake the beer, you put a whole bunch of little tiny bubbles, some big bubbles, some small bubbles, some little tiny bubbles, but all these bubbles have surface area. And you multiply the surface area, you know, compared to what was at the top by at least 100, you know, I don't know, maybe if you shake it hard and you get really small bubbles so that the surface area to volume ratio of the bubble is really high, I don't know, maybe you get 1,000 times the surface area for a little bit, at least until the bubble rises to the surface and pops. And if you get 1,000 times the surface area, then for at least the amount of time that you have that 1,000 times the surface area, you'll be carbonating 1,000 times faster than just sitting there. So there's no forcing going on. It's just the exact same thing going on with more surface area around the gaseous carbon dioxide. Anyway, that's what I did. I gave it a few shakes for, I don't know, 30 seconds, walked away for an hour, hour and a half, something like that. And now I'm going to hook it up to a tap and give it a taste. I expect this is going to come out very quickly since I've got all that carbonation in there. I just took about 8 ounces out, half a pint, right, to get the star sand out of my lines, but we'll see what happens. Oh, look at that, pretty quick. Now, I don't mind this because foam is good in a stout. That's why in a Murphy's or a Guinness, if you buy it in a can, it'll have the little gizmo in there that releases nitrogen bubbles all throughout the beer, which isn't anything really strange. What we're breathing here mostly right now is nitrogen. It's about 85% nitrogen, 14% oxygen, 1% everything else. So basically nitrogen, putting that little nitrogen thing in there is just putting air in there, only without the oxygen that might leak and ruin the beer. It sure the heck isn't a milk stout. That much I know. This, I'm definitely experiencing the dryness. There is no flavor to it, which is particularly bad. If anything, the flavor of this is kind of weak, which is making me think that this is something that is best consumed without the bubbles. Now I'm going to have to move somewhere because my battery's running low. Hang on. All right, I found a chart in chapter 14 of How to Brew, which gives a table of different names of enzymes. This is things that probably nobody needs to know, but it gives a temperature range within which these things thrive in terms of whatever it is that they do to your grain. And they have fairly low temperature ranges in terms of where it takes to kill a lot of these enzymes. So I went way beyond it, and there's really no doubt that the enzymes were killed by my boiling water. I almost feel a little bit weird saying this, but I like this beer. This is pretty good. If there's any one problem it's got, it's that it's missing carbonation. It still can use some time or some shaking under this thing right here, getting some carbonation. It has a kind of coffee feel to it, feel or flavor to it, even though there's no coffee of any kind in there. So if I make this dry Irish stout again, I have a hard time saying that. Irish stout, trying to put it all into one sort of word there. And I do it right, I assume it'll taste different from this. Who knows which I would like better. But it's kind of interesting to see that it didn't actually get ruined by having boiled those specialty grains. It really does have a coffee feel to it. If I've never had a coffee stout, but if I'd been in a bar or something and somebody said, "Here, taste this. Tell me what you think it is, what it's like," I would have said, "That's got to be a coffee stout, right?" So it's pretty good. So there's my book report on what happens when you boil specialty grains for a dry Irish stout.